This is exam 1 for Physics 202, spring 2013. Metallic object holds a charge of 3.8 times 10 to the minus 6 coulombs. What number of electrons? So we just say 3.8 is 10 to the minus 6 coulombs. And then 1 electron is 1.6 times 10 to the minus 19 coulombs. And that gives me 2.4 times 10 to the 13. And that's the number of electrons. That's A. Which of these statements is true about charging by induction? It cannot be done to conductors. That's not true. It can only occur with protons. That's not true. In fact, it usually occurs with electrons. Does not require contact between two charged objects. Okay, that is true. And it causes a bigger charge than by conduction. So the answer is C. Which of the following best characterizes electrical insulators? They move freely within the material. That's not true. That's for conductors. They are good heat conductors. In fact, they're usually bad heat conductors for the same reason, because the electrons don't move freely. They have a high tensile strength. That might be true, but not necessarily. And the charges of the material don't move, so D is correct. I have these two charges located. Which vector gives the electric field? All right. Due to this charge, the electric field is in this direction. Due to this charge, the electric field is in that direction. So the net electric field looks like that. So that is EA. 2-point charges are 4 centimeters apart, and then you move them to a separation of 2 centimeters. All right, so that means that the force between them is going to increase by 1 over r squared. So if I double r, that quadruples it, so it's going to be D. Excuse me, if I have r, the force, member, is K, Q, Q over r squared, and I'm taking half of my r value, so that gives me a factor of 4 in the force. I have a charged particle that moves to the left. That means that it's experiencing a force in that direction. In order negative particles feel a force that's opposite the direction of the electric field, so the electric field that causes this motion is to the right. That's in the positive x direction. So B is number 6. Electric field has the dimensions of newtons per coulomb. It's force per unit charge. All right, I have 2 charges. This one has a magnitude of 10 microcoulombs. It's positive because the field lines are coming out. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 field lines over here, and 4 field lines over here. That means that I have negative 4 microcoulombs. That's A. Consider this configuration of charges, which gives the force. All right, so due to this charge, my force is in this direction. I drew it big for a reason. I'll show you why. Due to this charge, my force is half the size of the blue force. It's in that direction. So my net force is the sum of those. It's going to look like that. So that is B for number 9. All right, what's the voltage across the capacitor C1? If I replace these 2 capacitors with a equivalent, it has 2C, so I have C and 2C. I have 12 volts down here. I want to know what is the voltage across this capacitor. It's the smaller capacitor, so it's going to have the bigger voltage. Remember, Q is CV. So for these, which have the same charge, if my capacitance is small, that means my voltage is big. But the sum of those 2 capacitors have to add up to equal 12. One capacitor is twice the other, so I know one voltage has to be twice the other. So I'm going to have 8 volts and 4 volts. All right, so the answer is D. This diagram shows a collection of charges. At what point is the potential 0? Well, here, the potential is not 0, because the distance from here to here is different from the distance from there to there. So those 2 potentials don't cancel out. Here, see, looks like the potential is 0. This distance is equivalent to that distance is equivalent to that distance, and that distance is equivalent to that distance. So the potential of all those opposite charges cancels out. Similarly, C, D, and E do not cancel out. I'll just do C. This distance is different from that distance, and D and E are not equidistant from those opposite charges. So the answer is B for number 11. What point is the potential greater? V is kq over r. So wherever r is smallest, the potential is greatest. That's A. Two pieces of copper wire, the same diameter. The length of wire A is twice the length of wire B. How do their resistances compare? Well, resistance is rho L over A. If L is big, R is big. So the resistance of wire A is twice the resistance of wire B. That's D. When you apply a potential of 3 volts to a particular electric device of 2 amps, that's the resistance then is 3/2 ohms. And then when you apply 6 volts, you get 4 amps. So that resistance is 6/4 ohms. Both of these are the same. That means that it is an ohmic device. Which of these has a greater current? Incandescent bulb or bathroom heater? All right, it's the heater. A lot more energy flows through this for a given time. It means you have a lot more electrons or a lot more current. Or you can also say that P is equal to I squared R. If P goes up, excuse me, not that, because R's are different for them. You have to look at it in this way. P is equal to VI. Here, the voltage is constant. If P goes up, I goes up by the same amount. So the higher power device has the higher current. Consider the circuit. What's the equivalent capacitance, voltage and charge on each capacitor? First, I just want to redraw it. As I come through here, across the battery, I come to this capacitor, which is in series with the battery. That's my 20 microfarad. And then I come here, and I break into 2 junctions. I go there, but then here, this breaks into 2 further junctions. So I can draw this instead as just 3 junctions, 3 branches. All right, in the first branch, I get this 2 microfarad. In the second branch, I get the 3 microfarad. And then in the third branch, I get 2 10 microfarad. And then they all come back together and go back to the battery. So I have a 2, a 3, and then 2 10 microfarad. 2, 3, and a 10, and a 10. All right, I can combine these 2 10 microfarad right here. That's going to be 1 over 1 over 10 plus 1 over 10. That's equal to 5 microfarads. And then I combine that 5 with the 2 and the 3. 5 plus 2 plus 3 is 10. So my circuit looks like this. I have a 20 microfarad, and then all those 4 capacitors go to a 10 microfarad. All right, I had 12 volts here. Just like we saw before, I have, where you have one capacitor that's twice the other, I'm going to have 4 volts across this one and 8 volts across this one. All right, I can go and find my equivalent capacitance. 1 over 10 plus 1 over 20. Let's see, that's 20 over 3, 6.7. All right, so my equivalent is 6.7 microfarads. And now I can fill in some values. I know that the voltage across this capacitor is 4 volts. That's going to be V5, 4 volts. I know that this voltage is 8 volts, and that that's also going to be across this capacitor and this capacitor. So that's 8 volts for C1 and C2. V3 and V4, I have 2 identical capacitors. Both of them share 8 volts. That means I have 4 volts across each. So that fills in the last 4 volts, 4 volts. And then for each of my charges, I know that Q is equal to C times V. So I just take the capacitance and multiply it times the voltage on each of those, and I get 16, 24, 40, 40, and 80 microcoulombs. And that's just taking the capacitance of each capacitor times the voltage that we found. All right, what is the electric field in vector notation at point x equal 1, y equal 1? The electric potential is given by this function. So my electric field in the x direction is the negative partial derivative of v with respect to x. And so that's going to be the partial with respect to x of this function. Let's see, so that is 2 times 2, which is 4 times y x, negative of that, and then ey is going to be negative of the partial of v with respect to y. And so that's going to be 2x squared minus 3. And so if I plug in 1 and 1, I get a negative 4 in the I direction. And this is going to be plus 1. 2 minus 3 is negative 1, plus 1 in the j direction. So for part A, the electric field in vector notation is going to be negative 4I plus 1j. And that's in newtons per coulomb. So that's the first part. An electron is placed at a point 1 plus 1 and then released, 1I plus 1j, so in that position. What is the velocity in vector notation after this certain amount of time? And then we assume that the electric field remains constant as what it was at the original position, although that's not exactly true, but we're going to assume that that's true. All right, so for part B, I know the electric field, so I need to find the force, and that's equal to Q times E. This is an electron, so it's negative 1.6 times 10 to the minus 19. There's negative 4I plus 1j. So that's, 6.4 times 10 to the minus 19 in the I direction, minus 1.6 times 10 to the minus 19 in the j direction, that's in newtons. That's the first part. Then we need to find the acceleration. That's just the force over the mass. That is this force that we just found over the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms. So that's each of these values divided by 9.11 times 10 to the minus 31. I get 7 times 10 to the 11th minus 1.8 times 10 to the 11th. And that's in meters per second squared. This is in the j, this is in the I direction. And let's see, I was looking for the velocity after a certain amount of time. It's my acceleration. My velocity is just going to be my acceleration times my time. I just wanted in vector notation, so I just multiply each of these times the time, which was 1 times 10 to the minus 5th. So that's going to be 7 times 10 to the 6th in the I direction, minus 1.8 times 10 to the 6th in the j direction. That's in meters per second. So that's the final answer. Consider this circuit and answer the following questions. What is the voltage for each resistor where they're in parallel, so the same voltage, 10 volts? 10 volts. What is the resistance for each resistor? Well, power is V squared over R, so my resistance is just V squared over P. So for example, 10 squared over the power, which was 100. So that's 1 watt. Or excuse me, 1 ohm, I'm sorry. Yeah, the one for the resistance. And here it's 10 squared over 50, which is 2 ohms. And then what is the current for each resistor? Well, you can just say I is V over R. That's 10 over 1 and 10 over 2. 10 volts over 2 ohms. So 10 amps and 5 amps. What is the potential at the top of the triangle? Well, potential is just sum of KQ over R for all the charges. I want to know what it is up here. That's going to be K times 2 times 10 to the minus 6. That's Q over R, which is 1 meter, plus negative 1 times 10 to the minus 6 over 1 meter. That's 9,000 volts. Don't forget the negative here when you're finding the potential. How much work is required to take a 3 microcoulomb charge at the top of the triangle? Well, work is just Q times delta V. It should be easy. You've already found delta V right here. So it's going to be 3 times 10 to the minus 6 coulombs times 9,000 volts. That's your change in potential, which is 27.027 joules. That's the answer for the work. Multiple choice answers.